So in today's lesson, we're going to look at some common fractions and how we can represent them as decimals. Okay, some of them are easier than others. So let's start with some really common fractions that we probably know the decimal representations to without needing a calculator, like maybe 1/2, maybe 1/4. Of course, 1/4 is 0.25, right? Even 1/3 is probably one that you know. It's 0.3, where the 3 repeats. Okay, so if you've forgotten that notation with the bar over, it means, hey, the 3 is actually going to go on forever. Okay, and we certainly should know all the powers of 10, since that's our number system, right? So a tenth is literally 0.1. Notice that's the tenths place. 1/100th is 0.01. Notice that's the 100th place. 1/1000 is 0.001, and then so on. I mean, we could keep that pattern going forever. Okay, so a lot of times with our students, we're going to build off things they already know in order to teach them something new. So let's say that you know that 1/4 equals 0.25. Then logically, if you have 3/4, so you literally have 3 1/4, okay, it should be 3 times that. In other words, 3/4 is going to be 0.75. That would be 0.25 times 3. Okay, so using that same logic, let's take another one we know. So if you know that 1/3 is 0.3, where the 3 repeats, then logically 2/3 should be how many times that? Should be 2 times that, right? So notice, even with this repeating decimal, we can actually just double it, right? So 2/3 is 0.6, where the 6 repeats. So let's take kind of some maybe less common fractions, but still ones that we would know that might repeat or not. So if I tell you that 1/9 is 0.111, where the 1 repeats. Okay, notice that time I decided to put a few ones before I mentioned that it repeated. Okay, then logically speaking, what should 2/9 be? Okay, well, 2/9 should be double that, right? So it will be 0.222, where the 2 repeats. And then 3/9 should be what? 3 times the 1/9, right? So 0.333, where the 3 repeats. We'll do one more, and then we'll just notice the pattern, right? Okay, so I'm just going to say etc. here. We could keep counting. 5/9 would be 0.5555 forever. 6/9 would be 0.666 forever, because 6/9, remember, would reduce to 2/3. So if I tell you that 1/11th is 0.09 with a bar over it. Now notice the bar is over 2 things. That means it repeats 09090909 forever. So logically, what would 2/11ths be? Well, it would be double that, right? So instead of 0.9 repeating, it would be twice that repeating, or 18. Okay, 3/11ths would be 3 times that repeating, or 27. 3 times 9 is 27, right? 4/11ths would be 0.36, and then so on and so forth. Okay, so a lot of times we build on things that they know, and we add in maybe things that they don't know as well. Okay, so notice, if I know one of these fractions, I get a whole lot of multiples of those fractions kind of for free, as long as I understand that I'm just multiplying them by something. All right, so let's look at one that maybe doesn't repeat. Okay, so if we know that 1/5 is 0.2, then 2/5 would be 0.4. 3/5 would be 0.6, right? 2 times and 3 times 0.2. And then 4/5 would be 0.8. So with knowing a little bit of information, we can actually say sometimes a lot about a different list of fractions. All right, so let's talk about kind of converting fractions to decimals and vice versa. All fractions can be written as decimals, all of them. But as we just saw, there may be a repeating decimal. And so we've been looking at repeating decimals with patterns, but it doesn't always have to have a pattern. It could just be a decimal that just continued on with different terms over and over. So I'm going to say with a pattern or without. Okay. But the same isn't true if we go the other way. Not all decimals can be written as fractions. So I want you to think about some decimals that are not able to be written as fractions at all. Okay, so some examples are pi. Okay, pi is a repeating decimal, but you can't write pi as a fraction. Okay, from college algebra, we have the exponential constant e. Remember, that's the number 2.718281828, and the 1828 repeats. That can't be written as a fraction. None of the square roots where we don't get a nice whole number result could be written as fractions. Okay, so I'm just going to say etc. This is certainly not the only ones. Okay, but things of this type cannot be written as fractions. So we're going to differentiate between two types of decimals today. One that terminates means to end, and one that doesn't. Now we're going to use a capital T to indicate whether it terminates or not. That's going to be our abbreviation. So this will be a decimal that ends. And then we call the decimals that don't end non-terminating. In other words, they don't stop. And we're going to abbreviate that NT. So this is a decimal that continues with or without a pattern. So it might use that bar notation, it might not. All right, so we can wonder, how will you know if a fraction will terminate or not? So as you're choosing fractions to work with in your class, maybe you want to keep it simple and make sure that it's a terminating decimal, or maybe you want to make it a little more challenging and include decimals that don't terminate. Okay, you kind of need to have an idea of when this will happen and when it won't. All right, so you're going to need a calculator for the next exercise. So if you don't have one with you, go ahead and maybe pause the video and go get one. But if the decimal doesn't stop on the calculator, keep in mind the calculator typically shows about 10 digits depending on what kind of calculator you have. But if the calculator, if the decimal doesn't stop on the calculator, we're going to assume it is non-terminating. Technically speaking, are there a couple of fractions that actually take 10 digits to terminate, but then they are done after 10 digits? Yes. Okay, but we're just going to assume that that's not the case, because most of the time that won't be the case. Okay, remember also that the calculator is going to round your last digit. Okay, so just a quick reminder, for instance, if I do 2/3 on my calculator, it's going to be 0.6 forever, okay? But notice, I know it's a little dark, but notice that the last digit actually bumps up to a 7 because the 6 after it is bumping it up, it's rounding it. All right, so I want you to take out your calculator and I want you to Pause the video. It's going to take you a bit. I want you to take out this worksheet that's called terminating and non-terminating decimals. And I want you to list the decimal as far as you can, okay? And then I want you to indicate whether or not it is terminating or non-terminating. Remember, terminating would mean that it stops. Non-terminating would mean that it doesn't. Also, if there is a pattern that you notice, I want you to use the bar notation. Okay, so like if there's a 3 that repeats, use the bar over it. Okay, so you're going to need to pause the video and take maybe 10 minutes or so and fill out this chart. Okay, and then we're going to compare our results and see if we have the same answers. All right, so here is my chart. I'm going to kind of slowly move it so you can pause the video and kind of compare. Okay. I don't think I can show it all on screen at the same time. Maybe I can. Oh, I think I can. There we go. All right, so hopefully you did that one on your own. The point of that was to do it on your own. I had a couple that didn't seem to repeat, like this one and this one, so I just wrote as many decimals as I could fit in the box, and then I rounded it. All right, so I want us to pay attention to the ones that are terminating. Okay, so notice which ones are terminating. Okay, so I want you to, again, maybe pause the video, and I want you to think about what you think the qualities are of things that terminate. So let's go over some things that terminate. 1/2 terminates, 1/4, 1/8, 1/5. Okay, so I want you to see if you can think of a pattern that would terminate for sure. Okay, and see if you can think about that. All right, so as we try to develop a rule for when something will terminate versus when it won't, note that all of these terminate, and then maybe you'll be on the right track. Hopefully you kind of brainstormed and thought about what you thought. So first let's talk about powers of 2. Okay, and so all of these will terminate. 1/2, 1/4, 1/8, 1/16, 1/32, and so on and so forth. Notice the bottom, the denominators are all powers of 2. Okay, so all of those terminate. Also, powers of 5 will terminate. So a 5th, 1/25, 1/125, 1/625, and so on. And then also 1/5 and the doubles of 1/5. Okay, so let me show you what I mean by that. So that would be 1/5, 1/10, 1/20. Notice I'm doubling, I'm starting with 5 and I'm doubling the denominator every time. All right, so let's talk about the rules. Clearly the rule has something to do with 2 and 5. And hopefully you saw that when you thought about it on your own. So the rule for whether or not a decimal will terminate, here's going to be our process. And it's important that you do this first step here. Lots of people forget this step. First, you reduce the fraction. So if the fraction isn't reduced, this rule won't work as well. So you need to make sure the fraction is reduced. The second step is we're going to factor the denominator. Okay, you can do that any way you want. We're going to use a factor tree for that. And here's where you determine whether or not it terminates or not. If the prime factorization, remember prime numbers are numbers that are only divisible by themselves in 1. So if the prime factors of the denominator are only 2s and 5s, then the decimal will terminate. If there is anything other than prime factors of 2 and 5, then the decimal will not terminate. In other words, if you fully reduce the fraction and then you factor the bottom and you get anything other than a bunch of 2's and a bunch of 5's, then the answer is going to be no, it won't terminate. All right, so let's do a couple. So will the following have a terminating decimal? So let's look at 3 over 40. Okay, so the first thing that I would want you to do is definitely reduce the denominator, or reduce the fraction, I mean. But notice this can't reduce. There's nothing we can do to reduce that. So I use a factor tree to factor out 40. So you can split up 40 into 2 factor pairs in a bunch of different ways, but I'm going to choose 4 and 10. In a factor tree, you don't stop until you hit prime numbers. And then I typically circle those numbers when they're prime. In other words, I can't go any further. 2 times 2 is 4, right? 2 times 5 is 10, and I can't break this down any further. Notice that this is only 2's and 5's. Okay, so our conclusion would be that since it's only 2's and 5's, 3 over 40 will terminate. Okay, so what about B? So what about 7 over 60? Notice again, we can't reduce this. It's already fully reduced. There are no common factors of 7 and 60. So if we factor tree 60, if we break that down into 6 times 10, and we break it down into its prime factors, okay, notice we have something other than a 2 or a 5, right? So we're going to say, nope, can't have a 3, right? So it's not just 2's and 5's, right? So that means this fraction will not terminate. The decimal won't terminate. Okay, so I want you to pause the video and try one on your own. I want you to try 18 over 750. See what you think about that. Does it terminate? Does it not? So hopefully you paused that and worked that out. The biggest thing here is that people would forget is to forget to reduce. This can reduce. Okay, so we can break this down into 3 over 125. And then we're just factoring 125. Sorry, that should be 5 times 25. Okay, notice this is only 2's and or 5's, so it doesn't have to have both. Okay, so that means 18 over 750 does terminate. Notice if you didn't reduce it, you would think that it didn't terminate because you would have a factor other than a 2 and a 5. If you factored out 750, it would appear not to terminate. Okay, so it's really important that you simplify that fraction first. All right, so let's talk about real quick, why does this work? Okay, the reason this works is because our number system is in base 10 and our place values are powers of 10. Okay, so our place values are literally 1/10, right? 1 100th, 1 1,000th, etc. So the reason 2 and 5 is significant is because 2 and 5 will always divide into 10 or powers of 10. So denominators that divide evenly into a certain place value. And remember, the place value is just a power of 10 always. Will not only terminate, but it will terminate in that place value. All right, so let's look at a final example, maybe with some multiple parts. So let's talk about 1/5. We know it terminates. We've already talked about 1/5 today, okay? But remember, the decimal for 1/5 is 0.2. And notice it actually terminates or ends in the 1/10 place. Okay, the first decimal place to the right of the decimal is the 10th place. Okay, but why does it do that? It does that because 10 divided by 5 comes out evenly, no remainder, in other words. So let's try another one that we know pretty well. What about 1/4? Now 1/4 takes 2 decimal places to terminate. Okay, so notice it terminates or ends in the 100th place. Okay, so let's try it. Notice 10 divided by 4 is not a whole number. Okay, but 100 divided by 4 is. Okay, so that's why it terminates in the 100th place, because it's the first time that we could divide 100 by 4 by the denominator. All right, so what about 1/8? 1/8 takes one more decimal place in order for it to terminate. So it terminates in the thousandths place, the third decimal to the right of, or the third digit to the right of the decimal. Okay, and the reason it does that is because 1,000 divided by the denominator of 8 comes out evenly, or as a whole number. Notice 10 divided by 8 is not a whole number. So the 10th place wouldn't work. Okay, and also 100 divided by 8 is not a whole number. It does not come out evenly, in other words. So the first place value where 8 would divide into it evenly was actually 8. All right, so one more I want you to try. Okay, so I want you to remember what 1/16 is, okay, and see if you can figure out what the explanation would look like. So pause the video real quick and see if you can do it. So it comes out to be 0.0625, right? It terminates in the 10,000ths place. And why does it do that? It does that because 10,000 divided by 16 comes out evenly. Okay, notice we definitely can't divide 10 by 8 or 16, right? But notice 10 divided by 16, 100 divided by 16, and 1,000 divided by 16 don't work. And by work, I mean they don't come out evenly. So not only can we say if something terminates, but we can actually be more specific and say where will it terminate.